Okay, I think we're going to go ahead and get started because Dr. Cipotas has granted me 30 minutes and I promised to go under, not over. We're going to talk about our first big class project. So there are really three bigger class projects in this term, as you'll see from your syllabus. The first is a mock DataJam project one, where you guys will form teams and you'll do a DataJam project. And this is a fantastic way to really get a feel for what are your teams that you're mentoring going through. I think you'll have no idea um, how much you learn by doing this yourself. Every year, um, DataJam mentors taking this course feel that they just learn an enormous amount and are much better able to mentor the teams they're going to mentor when they've done a mock DataJam project themselves. So we're going to start by talking about that. And then Alex Bauer and Lucas Troy, who designs the website and does all our social media posts, will be joining us at 6:15, and we'll talk for a few more minutes about things. But what I want to do to start with, and we have the DataJam Mentor course Google Drive open here, and you can see that on the screen. And there's a new folder in there today called Mock DataJam Project 1. And so I'm going to open that folder, I think. Yes. And in Mock DataJam Project 1, I wonder if we can get these listed.
So you want to use
Lit.
Yeah, just-
Yeah. Okay. Okay. So in Mock DataJam Project 1, all the instructions for doing this project are in the document, the Word document that says instructions. So I'm going to open that and let's see if we can make this a little bit larger.
So let me
Perfect. Okay. So we made it larger so everybody can see it on the screen, but you should be able to go into that folder and see it also. So Mock DataJam Project 1 is going to start in week 3. And so you'll see the very beginning is week 3, which is today. And what we're going to have you do sometime during the class period is to partner up with people in your class. So Pittsburgh people are going to partner with other Pittsburgh people. Students at Caldwell are going to partner at Caldwell because it just makes it a lot more logistically easy to be working on the team that is right there at your university, because all of the project is going to be done outside the classroom. We are not having classroom time for doing your mock DataJam project, but you have the next 3 weeks to work on it, and it should go fairly smoothly. And you should be able to work on it together remotely. I'm sure that many of you won't need to meet in person, but you can set up a Zoom call or something like that and meet. So what we want you to do today is to form mock DataJam teams. And remember, the rules of the DataJam are there have to be at least 2 people on a team. We can't have a single student working by themselves. And then you're going to go to the mock DataJam team log, and you're going to put in the names and email addresses of the students on each team and a team name. So I'm going to go back here to all the documents that were in the Mock DataJam Project 1 folder, and you'll see an Excel spreadsheet that says this is a Mock DataJam log. And let me make this a little bigger. Okay, there's not much in here at this point, but all of you need to come up with a team name. So you're going to make teams and you're going to create a team name. I don't care what it is, but we can't have 2 teams named exactly the same thing. So look at the teams that have signed up before and make sure you're naming yourself something unique. And then you can put the students there, and you want to use different rows for different students. So if you have 3 students on your team, you want to use 3 rows for the students and the student email addresses and the proposal title. It shouldn't say date. I'll do that. Proposal title. So you want to put the title of what you're working on. So what you'll need to do is talk to each other. You may not be able to fill this out tonight, but you want to form a team, and then you're going over the course of this week to make sure that you have a discussion about what your research question will be and look for data sets so that you can put down a title of what you're going to work on. We're going to go back to the instructions. That's what you need to do this week. You'll kind of spend the week working together and coming up with a project title. By next week, so you have a whole week to do that, kind of come up with a research question, put your title in and into the log, and then you're going to need to submit a proposal. There is a proposal form right here in the folder. You see there's the proposal guidelines, and then there's the proposal template. If you look at the proposal guidelines, this is exactly what DataJam teams both at the high school and the community college level get. They get these guidelines. And so you just need to follow exactly the guidelines that the students follow. And then you need to come back and fill out the template. And you'll see the template has the project title, the team members, a written couple sentences about what your research problem is, why it's important, your hypothesis, and the data sets. So what you want is links to the data sets that you're going to use. The reason we give you a whole week to work on this is it takes time, and it takes your DataJam teams a lot of time to do this. They come up with a research question. They frequently do this by each person on the team kind of coming up with a few ideas, and then a discussion of what does everybody like? What do people want to do? And then they have to go look for publicly available data. And you're going to have to do exactly that. And this is the hardest part of the DataJam, is finding data sets that you can use to analyze to answer your research question. And a really good thing about having you go through this process is you will have new empathy for how hard this is for your teams. And you'll also have strategies that you have tried. You want to remember that right on the DataJam website, there's a tab called Data Sets, and there's huge number of links on that data sets page to publicly available data sets. So we've made probably close to 30 data set guides. This is great. Yeah, so we're on data sets now. And if we go to data set guides, you'll see that the data set guides many of these have been made by mentors as their end of term project that they work on. The others have been made by professors that are very supportive of DataJam at the universities we work with, or graduate students or postdoctoral fellows that are supportive of DataJam. DataJam has a big group of academic people at a number of universities that really like the idea of DataJam, and they've made guides. So the first guides look at biomedical research questions. So you can see this is a guide about asking questions about vaccines. And if you open this guide, you're going to, I think I can click through it. Yeah, here we go. They're all done in kind of a PowerPoint format. We try very, very hard to have it be digestible, even by high school students. So the beginning of each guide tells a little bit about the research topic. So this is going to tell some information about vaccines. So the history of vaccines is one side. The myth that vaccines cause a problem like autism, 6 different types of vaccines, inactivated vaccines, and it goes through. And then it says a research question that you could ask is look at vaccination. So how often are vaccinations given in rural versus urban settings? If that was your research question, here's a useful data set from the CDC. And if you click right where the arrow says, it will take you to the CDC data set. So the nice thing about the guides is it takes you right to the data set, and it tells you about the data set, and it actually tells you how to use the data set to answer your research question. So if I go back here to the data sets page, I can go back here. I'll close this. Okay. So there are biomedical questions, and there's a lot of different biomedical topics. Then underneath that, you'll see that there are guides on climate research questions. We've had lots and lots of teams do projects that ask questions about climate and climate change. It's been a popular topic. There are guides on how to ask questions about economics and finance, like asking questions about inflation. There are guides on education research, so asking questions about special education. That's surprisingly been a very popular topic for high school students because high school students live in their microenvironment, their school, and they're very likely to ask questions that they know something about. And so they know that there are special education programs. And so it's not surprising. Community college students and high school students have used the asking questions about careers and where would you go to college to pursue a particular career. And we have data sets on those. Social research questions, one that's been very popular is asking questions about gun violence. And you can imagine that because a lot of communities are experiencing more gun violence in the last decade, that this is something that students know quite a bit about. Once you get past the data set guides, the data set links themselves, they aren't guides, they're just links to publicly available data sets, are divided into categories. So the first category is international data sets. One of the largest and most popular data sets is Kaggle. And Kaggle has data sets on an enormous amount of topics. And if you have any question that is comparing the United States to other countries, I would go to Kaggle first. I mean, there's also data.world, the World Health Organization, and a number of different data sets. Under that, there's national data sets. And if you're asking questions comparing different states or different regions of the country, again, on almost any topic, you can go to data.gov over here, the US Census, us.gov. If it's a biomedical question, you can go to the Center for Disease Control, the CDC, or the NIH. If it's an environmental question, the EPA has data sets. And then under the national data sets, there are regional data sets, and all of the states that we've currently had DataJam teams in are listed there, but not all states. We don't have all 50 states. We've just tried to populate it for the states where we've had teams so far. We expect to have new states this year, and we'll work on making new guides. But I want to point out here for California, this first guide is data collected in the San Francisco Bay Area. And then there's something that looks exactly the same, but it says Guide 2. It has a big red set of letters. A DataJam mentor made a guide for how to use that San Francisco guide. So it's a guide to that data set. So we not only have a link to the data set, we have a specialized guide to using that data set. So this should really, really help you in coming up with research questions. If you want to think about what have high school and community college students done as DataJam projects, if you go to the DataJam page and go to the bottom of it, all the past projects done for the last 10 years are listed there, and you can download the posters, all the posters for the last 10 years. So you can start to get a feel for what are the kinds of research questions that people have done in their DataJam project. Okay, I'm going to go back here. You'll have this week to work on your proposal. You'll submit your proposal into a proposal folder. So let's see if I can get back here. No. Hang on, here we go. We're in the mock DataJam Project 1 folder, and you can see that there's a folder now for submitting your proposals. At the end of the mock DataJam period, you will be able to submit posters. So remember that DataJam teams submit a poster, and then a month later, they give an oral presentation. For your first mock DataJam project, you're going to submit a poster. For your second one, you're going to give a presentation. So you don't have to do both for each project. We're just trying to give you experience with doing this. And then we're developing a new scoring rubric right now. The members of the board of directors of the DataJam, that should be done by October 1st, when you're going to present your first project. And each of you is going to get to score all the other team's projects using the new rubric. We're super excited about this because I think you will give us feedback on, was this rubric easy to use? Was it horrible and we need to work on it some more? That's always a possibility. But I think it also will teach you, how will the teams you're mentoring going to be judged? So you'll be a better mentor because you'll understand exactly how they'll be judged and what needs to be in their proposal. So if we go back, let's see, guidelines. No, I'll get there. Here we go. So on week 4, you're going to put in the title. That's next week. On week 5 in the log, you're going to put a few sentences. This doesn't need to be much, just a summary of what you've done. We've done these analyses. So far, we're finding this. We just want to see that you're progressing. And then on week 6, you need to submit your poster in the poster folder before class. Each team is going to get 10 minutes to present their poster. We'll have questions, but it kind of depends on how many teams we have, how many questions you'll be able to have. And then you'll be able to score everybody's poster. And you'll know a lot about DataJam projects at the end of this. Are there questions? Pittsburgh? No? Caldwell? Okay, let's see if we have Lucas. Do we have Lucas and Alex on?
Yeah, I'm here, Dr. Cameron.
Indeed.
Okay, great, great. I'm going to switch gears and now we can probably stop sharing this.
You don't need that?
We don't need it anymore. We finished with that. So one thing we asked you to do last week is Alex asked you to go to the sign up sheet and sign up as a mentor. And all 33 of you did it. And so Alex is smiling over there, I hope, and feeling very, very happy. Everybody did it. And then as of last night, we had about half of you submitting your bio, your picture, and many of you submitting a 30-second video. The bio and the picture are going to go on the website. And Lucas is the person who handles all the website logistics. So he's taking your bio and picture and putting them up on the website. We already have a high school team and we already have a community college team all signed up, and their mentors are, their advisors are already trained, and they're asking for mentors. And we've said, okay, mentors are coming. Not yet, but they're coming. So they really want to see who the mentors are. I sent a reminder out today, and 5 more of you submitted, but I think that means we have 24 submissions at this point, and we need the other 9 of you who have not submitted your bio, your picture, and your video to do that, because Lucas will work hard to get this information up so that people they want to see, not the old mentors, and we'll get the old mentors off of the website by this weekend. We want to put the new mentors up, and they want to see who you are. The 30-second videos are going to be used in our social media campaign because we're starting to get teams thinking about forming and being DataJam teams, and we really want to reach out on social media. So, Alex, do you want to say a few words? And then we'll have Lucas say a few words about our challenge.
Yeah, so thank you all for submitting. Everybody signed up the initial form, and then we're missing just a couple people for the bio and 30-second video. So those bios are going to go on our socials, which is why we asked for your handles to both Instagram and LinkedIn. So you'll see there that throughout probably the rest of September, October, possibly into December, your name and picture and bio are going to go up on our socials to kind of highlight your participation. And if you submitted a 30-second video, that's also going to go up, which is really nice because that gets us a huge amount of engagement. And all we ask for you to do is share with your friends, right? We want you to know that we're proud of having you as mentors, and that like it would be great to have other people know that you're also doing this volunteer work, and we're very happy to have you. So thank you all for doing that. Let's get the last few in so we can make sure that everybody gets to be highlighted on there, and I'll see you on the Instagram.
So Instagram in particular, high school students follow it like crazy. They love hearing about mentors. And you can imagine you're just a little bit older than they are. They're way more interested in you than they are in old people like me. So we use the mentor bios videos to really engage the high school students. On LinkedIn, we have a lot of college students who very much follow that. Lucas, you want to talk about our challenge?
Yeah, so this semester we're starting with a new challenge for the mentors, and this is really to y'all's benefit. So I'd love to see some good participation here. Our goal by the end of the semester is to reach 250 followers on Instagram. I think we're currently at around like 117 or so. So if you're not following the Data Jam on Instagram, the handle is the underscore Data Jam, I believe. Let me make sure. Yes, _DataJam, one word. If you're not following, make sure you're following now. If we get to 250, I believe for the end of the semester presentations, we're gonna do a pizza party in everyone's
We're actually, the end of the semester presentations is a very busy time, but the week before, we have a lecture on how to give presentations. And I will cut that in half. So we can have a pizza party and we can socialize and interact and get to know each other better and have fun. So if we can get to 250.
Yeah, so there's food involved, which is a huge proponent, I think, for a lot of you, hopefully. A good snack as well. So the Data Jam, right? Make sure you follow it on Instagram. There's roughly 33 of you, so in order to get to our goal, right, just you need to ask like 2 or 3 friends each to follow as well. This is really going to expand our reach and help get us out there to more people so that we can do more of these and have better challenges in the future. So thank you all for your participation in advance. And I look forward to growing this community with you guys.
Any questions for Alex and Lucas? Okay. Thank you. We really appreciate you showing up. We're done. Oh, and in 26 minutes.
Breakneck.
I know.
Sharing.
Okay, how are you doing? Doing well?
Good.
Are you doing well? Now, I know that we're covering a lot of things in a short period of time. We're more or less covering the high level. But if there are things that you're not really able to follow, or there are things that you want to read some more stuff about those topics, feel free to reach out. So I'm more than happy to share some extra resources regarding this material. Now, the topics covered in today's lecture. So basically, we're going to dive into why correlation does not necessarily mean causation. So it's easy. Once we start working with the projects, we get excited. And also the high school students, they get excited about their findings. And then it's very easy for them to talk about causational relationship between the variables. So it's your job as a mentor to guiding them and put them back in the correct track. And then we're also going to talk about publication bias. So these are 2 ways that publication bias will arise. And these will be related to the projects that the high school students will be doing. And it's good to be aware of those 2 sources of bias. Now let's see where we have been and where we are going in today's lecture. First, we started by saying, how do we assess correlation? So during the first week, we gave the intuition, we gave them, let's say, the definition of the correlation. We got a little bit into the formula, how do we calculate correlations between 2 candidate variables. Then we answered the question, did this correlation arise by chance, or does it reflect a genius relationship? This goes back to our statistical inference, where we're talking about a hypothesis testing, and I wanted to see if indeed that correlation is statistically significant. Now, what we're going to cover in today's lecture. Even if we have identified a genuine relationship, a correlation, or let's say association, why is that typically not convincing evidence of a causational relationship? Why I cannot really talk about causation anytime we detect an association between the variables. So we're going to see some tools for more credible assessing causal relationships. And then we're going to think about all the tests conducted and the possibility of selective reporting. I want to start this class with this motivating example. So this is a motivating example related to charter schools. Now, for the people that they're not aware or they never heard of the charter schools, basically are some public funded schools where they have a little bit of more, let's say, independence compared to the public schools. And then they have different procedures, how they can recruit people and a little bit of their, let's say, what are they going to cover in that school. Now I remember Professor Cameron mentioned last year that actually we have some teams from this charter school, right?
Last year we had 4 teams from Price School, which is on the UCSD campus.
Yeah, so actually this is created by UCSD,
Right.
specific charter school. Now there's always kind of a topic of debate whether charter school improves the academic performance of the students, and there's always again that discussion about inequality in education. Now what I want to do in today's lecture is let's start by seeing this figure, which shows the percentage of students who pass a standardized test at this specific charter school compared to the San Diego City School. So you can see I have 2 different exams about mathematics and English language, and then I have the percentage of students who pass this standardized test. And then I have a side-by-side bar graph where I'm showing you the results from the charter school compared to the San Diego City schools. Now, what do we observe? Regarding the passing percentage, if I compare that specific charter school compared to the San Diego City School.
The San Diego City School has
Sure.
lower passing rate.
Okay, what you observe is that, okay, there is an association between these two, right? And what you mentioned is that the public schools, they have lower, right, passing grade compared to that charter school. Okay, now the next question that we can ask is, does it mean that the charter school itself causing or making the students achieve higher scores compare, let's say, more students passing the courses compared to the charter compared to the public school? So does it mean that the charter school caused that increase in the number of passing students for those 2 tests? Why? I want to hear a little bit your thoughts on this topic.
Because correlation doesn't mean causation.
Why?
Because there could be other.
Because I can see from the graph, right? The charter school has higher percentage proportions there.
Yeah, but there it could be like you're not looking at what kind of kids are enrolled at the schools.
Okay, so now you are mentioning some other variables that they may affect the observed relationship. And you mentioned about
Maybe the
type of students.
maybe the home life of the students going there.
Okay, the home life of students that they join these 2 different type of schools. Is there anything else that you can think? And actually, I want to hear from Caldwell School. Can you think of any other variables that they may affect the observed relationship? So students from Pitt mentioned that maybe the home life of these students is different across those 2 different types of schools. Can you think of any other variables from Caldwell University? Can you think of other variables that they can affect the observed relationship?
What do we got? Someone. What could be another variable?
Are there any other factors
Anything
that they
else?
may affect? Okay, someone from Pittsburgh, maybe? Yes.
As it is, this graph only shows mathematics and ELA. You don't know if the Price School bombed on civics, for example.
Okay, you're saying we need to maybe look some other exams, right? Not
Yeah.
just these ones. Okay, I agree. Any other variables, maybe from Caldwell or in Pittsburgh?
The first question that came to my mind is like, what are the enrollment totals at these schools? Like, I would imagine that the San Diego City schools would have a much larger body of students compared to the charter school. So that may be influencing these statistics that we see on the chart.
Okay, so basically the charter school will have more selective bunch of students, right?
Mm.
So that's why we have this. Okay, that's a very good point. Yes.
Maybe the better school is next to a library and the other one's next to like some basketball courts or something.
Sure. Actually, here, we can't think of any other variables that may affect. Maybe I don't know, their race, or I think you mentioned last year that usually they're first generation.
Yeah, so really
Students.
interestingly, in order to get into Price School, you have to be a first generation American. And I've had a number of first generation Americans over the years as undergraduate and graduate students working in my lab. And I can tell you from experience, their parents put enormous pressure on first generation students. So I think that one variable is that the Price students are getting a lot of pressure to do well in school from their parents because they are the first generation Americans. And that isn't uniformly the case in a public school
Yeah.
population.
Yeah. So to be fair, actually, in order to make sure that the results are, let's say, representative, what we should do is I need to get the same students attend the charter school and also attend the public school and then compare the results. This is what we call counterfactual. Counterfactuals, of course, we cannot do that. Cannot have the same student attend both of the schools. But let's see what I'm trying on the next slide. So to attend the specific charter school, so basically you apply, and then if there are a lot of students that they want to get into that charter school, there is a lottery. And then what I'm comparing here, instead of comparing charter school students and public school students, what I did is I create some graphs that I compare the standardized test scores of students who won and the ones that they didn't want the entrance to that charter school. And here I look at 3 different subjects: language, geometry, and physics. And on the y-axis, you see the average score in these exams. Now, what do you observe? And now, this time I was somewhere from Caldwell. So what do you observe from this chart? Before, we could see that there are very big differences between this specific charter school, and the public school. Now, what are the observations based on this specific side-by-side bar graph?
What are the observations? What do you see? The mic's open. Someone.
The comparison school outperforms Prius when it comes to geometry. And then the average.
Okay.
Not,
Good, speak up. So she's saying the,
Yeah, we could hear what she said. So exactly. So
Okay.
here what we observe is that for geometry, even let's say the public school performs slightly better than the charter school, but overall, I don't really see very big performance differences across those 2 different schools. So this is telling us that the charter school itself is not necessarily helping or hurting the students regarding their performance. Now, this leads us to our discussion about confounding variables. And let me formally define what we mean by confounding variables. A confounding variable is any variable that confuses the relationship between 2 variables as a result of being related to both. So let's say I have an observed relationship. Let's say I observe the relationship between the performance and the type of the school. The confounding variable is a third variable that can affect both of the observed variables. And you can see here the diagram. So I have the observed relationship and I have another variable, and then these could affect both of these variables. So anytime we are trying to make causational conclusions about a specific scenario, we should always ask a question: are there any confounding variables that they may really impact the relationship, the observed relationship? And this will be very important when you're dealing with the high school students. And let's do one practice here, and you're going to do some more during today's handout activities. Let's say a retrospective analysis of fires in a major city found that more firefighters who responded to a fire, the more firefighters who responded to a fire, the more damage was caused. Does having more firefighters at a fire cause more damage, or is there a missing confounding variable? So we observed that if there are more firefighters, then there are also more damages. It doesn't mean that maybe we shouldn't have really sent so many firefighters because this can cause more damages. Yes.
No, because it's likely that if more firefighters need to be at a fire, then the fire is probably bigger, stronger, like more dangerous.
Exactly. Now you mentioned a confounding variable, which is basically the severity of the fire. If the fire is bigger, then we're going to recruit more firefighters, and of course the damages may be bigger compared to, let's say, if you have a small fire. So in this scenario, we have, let's say, the severity of the fire as a confounding variable in the relationship. Now, when, let's say, you deal with the high school students, these will be a nice guidelines that can help you to answer different kind of questions and explain to the high school students and guiding them on the correct direction. The first question that you need to ask anytime you observe a correlation, anytime you see a relationship between different variables is there actual correlation be observed? How do we know if there is indeed a correlation in a scenario? This is our discussion during the first week of lectures. I want to have variation in both of the variables, and then we have seen some metrics to measure different correlations. Now, the second question that you need to ask is the correlation statistically significant? Does the correlation arise by chance, or does it reflect a genuine phenomenon in the world? So this goes back to our second week lecture, where we're talking about a hypothesis testing. Once you detect a correlation, you can do a hypothesis testing to see if indeed this result is statistically significant. You didn't get it just by a random chance, but indeed there is such a correlation in the data. Now, the third question that you're going to ask, and this is related to this week material, is this correlation convincing evidence of a causal relationship? And to help and guide the high school students to answer this question is to try to talk about confounding variables, explain to them the idea that there may be some other variable, a third variable, that may affect both of the response and the explanatory variable. And this really helps to have some examples in mind where you can tell to the high school students and explain to them and guide them why some scenarios you may have some other variables that they may affect the observed relationship. Now, if you have identified a relationship that does not make sense as being causal, you can ask the following questions. Is the relationship spurious, or is there a confounding variable? Actually, we're often presented with some relationships that don't make any sense. And in those scenarios, and we're going to see some examples in a minute, in those scenarios, we're not even getting into the discussion about confounding variables. So some relationships are very kind of random. They don't have any meaning, or they don't really make any sense. So we need to be careful about those spurious relationships. In other words, some fake relationships between the data. Of course, these will help us if I have, a domain knowledge, I have some expertise in that setting, so you can see if indeed this relationship makes sense. Now, if there is a confounding variable, then how can we measure it, and how can we incorporate that in our analysis? And this is what we're going to do on the next part of the class. Now, before I get into what do we do with the confounding variables, let's see some fake correlations. So I got some correlations from a textbook called Spurious Correlations. And here, what I want you to see, we have the sociology doctorate and the space launches. So here I have basically some time series data. And what I want you to observe is that both of these ones, they are following a very strong, let's say same trend, the same pattern, very strong pattern along the x-axis. Now, if I go and calculate the correlation, you're going to observe that the correlation is 0.789. So this is telling us actually that there is a very strong linear relationship between the variables. But does it mean that sociology doctorates causes the space launches, or is that relationship meaningful in this setting? Does it tell us anything? Not really, right? These are kind of very random. Now, let's say you observe between 1997 to 2009, But if you observe from 2009 to 2025, you may observe no relationship between these two variables. These relationships are very random. These are kind of random patterns that can be found in different datasets. Here I have one more example. It's a Nicolas Cage films and swimming pool drawings. So you can see that, again, they're following kind of the same pattern from 1999 to 2009. The correlation is 0.66. Have a moderate correlation between the variables, but doesn't make any sense, this observed relationship. Doesn't mean that if Nicolas Cage, I don't know, get into films, it means that we're going to have more, or the swimming pool drawings, or is there any kind of meaning in that relationship? Not really, right? So the takeaway here is that not all correlations will make sense. And in these scenarios, we are not even getting to the question of, are there any confounding variables? Because the relationship itself does not really make any sense. So it's something that we need to be aware.
Can I make a comment?
Of course.
So the reason that we're actually spending a really significant amount of time in this is you will face this. If you mentor for the DataJam, you absolutely will have teams where correlations are the main analytical strategy that they use. And high school students, as a rule of thumb, think that a correlation means a causal relationship. And you have to work really, really hard with them to get them to understand that isn't true. And it's important because when their project gets judged, the judges will be all over them if they are making the assumption that because there was a correlation, it was a causation. But that's hard for high school students to grasp. What we find is when we first started the DataJam 12 years ago, I would say 90% of the teams, their main analytical strategy was to do correlations and regressions. Now, it's probably 60% of teams that do that. However, it has always been that at least half the teams interpret their correlation as being evidence of causation. So you can't mentor for the DataJam and not face this issue. And so we're really trying to prepare you to be able to work with your students and teach them these really important concepts that just because you see a correlation, it isn't a causal relationship. But I don't think we've ever had a mentor who hasn't dealt with this.
And especially once you get excited, once you get results, you really get excited about the findings, right? And you always want to say something more of what you have. That's why we ended up to that causation. And actually, that's very common even in research, let's say among journalists. I have seen a lot of articles or a lot of, on the TV where they're talking about causational relationships. They're not really there.
I mean, I'll give you one of my very favorite examples, and maybe it's my favorite because it was when mentors went in person to local schools, and I happened to be there when this high school team came up with their research question. Their research question was, does having a Starbucks right near your school improve the grades of the students? And they thought that was likely to be true because they would be getting caffeine while they were studying. And it was fun to be at Starbucks, so they would be there studying more. I was surprised to see they thought Starbucks was a place where you would go study, but that was what they thought. And they were shocked when they didn't get a correlation. They plotted how far a whole lot of high schools in Pittsburgh were from Starbucks, and they didn't see a correlation. And the mentoring tried to get them to think of what are other variables that could influence GPA or could influence your test scores? And they couldn't come up with anything. I mean, the quality of the students coming into the school, the quality of the teachers, the quality of the classes. They didn't come up with any of that. They were so wedded to their Starbucks hypothesis that they just couldn't see anything else. And it was really educational to watch their thinking process. And so I think you're right. I mean, you get wedded to what your hypothesis is. And we can laugh
take it
because it's
personally.
kind of silly, and you think, oh, that's high school students. But there are lots of full professors that get wedded to their hypothesis, and then they don't know what to make of their data that doesn't show that things are related the way they think.
Pegaway, let's build more Starbucks near schools.
I know.
Okay, any questions? Any comments? Any clarifications? Okay, now the next question before, let's say, the handout or today's handout is, okay, what do we do about the confounding variables? So we know that confounders bias our estimates of causal relationship. So these bias can be controlled by adding that variable in our linear regression. So here what I want to show you is, this is the linear regression that we feed anytime we have two variables, response explanatory, and I want to feed a linear regression for these two variables. Now, anytime there is a confounding variable, what we could do is we can add an extra term in our linear regression, and we're going to see how we can deal with that confounding variable. Now, I want to show you another example here. So here I have on the x-axis the height, and then on the y-axis I have the income. So in other words, I want to see the effect of height on income. So I have some data from US survey conducted in 2014. Now in this graph, with those black dots, I have the data from for women, and then with white ones, I have the data for men. For now, just ignore the sex, let's say a sex assigned on birth. Let's ignore that variable in our analysis. Let's look the spiral plot, and I want to hear from you, what do you observe? What is the relationship between the height and the income, ignoring the sex? In other words, is there a positive, negative relationship between the variables? Is the relationship linear? Is it curved? Is it strong? Is it weak? What do you think about the relationship between the height and the income? Let's start with the direction. Does it seem to be a positive or negative, the relationship between the height? So in other words, as I'm increasing the height, what do you observe about the income? Do you observe an increase or decrease? And maybe for some that didn't talk to me, either from here or the Caldwell.
Speak up.
Sure, someone from Caldwell?
Increase.
Increase, right? So there is a positive relationship between the variables. Okay, what about the form? Do you think it's linear? Do you think it's curved? Roughly speaking, the general trend, the general pattern. So what do you think? Is it curved? Is it linear? From Pittsburgh? Roughly speaking, yes.
Roughly linear.
If I want to summarize the general pattern, if I pass a straight line, it will be, roughly speaking, a summary of the relationship between the variables. And then regarding the strength, there is, I don't know, moderate strength for that linear relationship between the variables. Okay, now what we're going to do is, let's try to feed a linear regression. So here I feed the linear regression. I found the best line that can summarize the data. And in this scenario, I use Excel. So our beta was basically 15K. In other words, the slope was 15K. So in other words, for an additional foot of height, we observe a 15K increase in the income of that individual. Now, does it mean that height causes the income to increase? Or are there any confounding variables also in this scenario? What do you think? Yes.
It's often stated that if you're eating, be able to grow actually taller, eating more, usually assign asterisk of like the healthier population or more access to food.
Okay. Okay, yeah. This could be a variable that can affect basically both of these ones. Anything else? Any other variables that we, yes, any maybe from Caldwell?
Survey size.
What size?
Survey.
Survey size. So what do you mean by survey size?
If we were to increase the survey size, then the results would change.
Oh, okay, we could ask more, right?
Sample
We could
size.
ask maybe more people, and then we observe different trends, sure. This could be a problem in this specific analysis. There are many issues that they may rise here. They may have other factors, not necessarily the height, but we know that, for example, sex, the variable that I'm going to consider in the meeting, this can also really impact your income. So it's not necessarily the height itself, but there may be other variables, or maybe there's some, sex discrimination, yes, between women and men. Yes.
You could also consider the age of the people you
The
survey,
age, of
because
course.
people can get work permits, I know at least in Pennsylvania, at the age of 14. So a 14-year-old probably working minimum wage is not going to be making the same as a 38-year-old who's in a career.
Yes. So here are a lot of confounding variables. But for the time being, let's just consider, let's say, the variable sex. Let's say I feel that sex can really impact the income of the individuals and also the height. We know that usually men on average are taller than the woman. And not only that, but men earn higher income on average for some unrelated reasons. Let's say what I mentioned before, let's say sex discrimination or for whatever reasons. Now let's try to see how we add this information in our data analysis. So what I'm doing here to address this concern, let's say about the confounding variable, I'm thinking I'm not going to have one linear regression for the whole data set. Let's fit two linear regressions. I'm going to use the data for women to fit a linear regression, and then I'm going to use the data for men to fit another linear regression. So here, these are the lines that I draw when I fit independent linear regressions. The linear regression for men, for men are the white ones, and the linear regression for the women. Can you think of any drawbacks of this analysis? Sure, we can analyze them separately, but can you think of any issues that we may have here? Are we missing anything if we are analyze them independently? And actually, this is related to what the student at Caldwell University said about the size of the sample base. Do you have any comments here? What do you think? Why I cannot fit two separate linear regressions? Think about it. Here I have in total, I don't know, maybe 30 observations. And then I'm going to use just 15 observations for one model, 15 observations for the other model. Sample size increase our accuracy for the estimates. The more observations I have, the more accurate my estimates will be. So basically, I'm losing some information if I fit two separate linear models in this specific scenario. Also, another issue is that we don't really, let's say, account for shared patterns across those two different groups. There may be some similarities. Of course, there may be some differences. But what about the similarities across those two different groups? If I fit two separate regression lines, then I'm losing any kind of common things, common pattern that exists across those two different groups. So there are different drawbacks of fitting two, let's say, separate linear regressions. Now, what we're going to try to do, and that's what I'm going to ask you to do in our today's handout, is let's try to fit one regression. we're going to have our regression. Let's say here I have the income versus the height, but I'm also going to consider the sex as a variable in our analysis. Now, the sex here will be denoted as a what we call dummy variable, a binary variable. Let's say I'm going to have 1 if it's a male, 0 if it's a female. So in other words, what will happen is that even though you're feeding one linear regression, you're using the whole data set for the linear regression, at the end of the day, you're going to get 2 separate lines. 1 for women, 1 for men, because I have that dummy variable. 0 for men, 0 for. That's what I'm doing on the next slide. So let's say here I feed one single linear regression. I'm considering the response to be the income, the explanatory variable to be the height, and I'm also adding the sex as an explanatory variable in our linear regression. Now, in this scenario, we're going to estimate 3 parameters. The first one will be the intercept, similar to what I had before. I'm also going to have the slope, and then I'm going to have the difference between, let's say the distance between these 2 lines. And I'm denoting here by gamma hat. This would be, let's say, in my model here. So I'm going to have the y-intercept, I'm going to have the slope, and this gamma will be the distance between these 2 points. Now, if I fit this single linear regression, I'm going to observe that the slope now changes from 15K to 8K. So in other words, if I feed a linear regression with both the height and the sex, I observe that now the slope is 8K, meaning that if we increase the height by 1 foot, then we're going to see an increase of 8K for that individual. Now you can see a quite big difference between the slope that I had before, 15K, and the slope that I have now, which is 8K. In these scenarios where there is a very big difference between the estimate of the slope, we're going to say that indeed that confounding variable could get into our analysis. If you add the confounding variable into your linear regression and the slope does not really change much, it means this variable does not really affect the relationship. And maybe we can exclude it for our data analysis. Now here I'm giving you a sketch of, let's say, the steps that we're going to follow to deal, let's say, with confounding variables. And once I'm done with this slide, then I'm going to ask you to go into the handout. Now, it is possible that a variable we think is a confounder does not actually confound. We may come up with some confounding variables, but these may not really impact significantly the observed relationship. If this happens, then there's no need to leave this variable in our regression because it's not doing much and is not much of interest in this specific scenario. Now here I'm giving you a very simple steps that we can follow. These are not, let's say, strict steps that you need to follow. These are more like rule of thumbs, very simple steps that we can follow to see if indeed that confounding variable plays a crucial role. So what we're going to do is first, we're going to fit the original regression without the confounding variable. We're going to estimate our alpha. We're going to estimate our beta. And the most important thing is, look, what is the value of the beta? Then you're going to add the confounding variable into our linear regression. Now you're going to have an extra, let's say, estimate here, which would be the gamma. But I want you to take a look again on that beta. Now that beta may be different to the beta that we have before, may have different value. And I'm going to denote that by beta star. Now, if the beta star is more than 2 times the standard error, and how can you find the standard error? When you have our linear regression, you get the coefficients. On the next column, you get your standard error. If the new slope is more than 2 standard errors away from the previous slope, from the previous slope, this is telling us that it has a very big difference. Our slope significantly changes across those 2 different models, which means that the variable that you are considering is indeed a confounding variable, and then should be included in our model. It is a confounding variable. It really affects the observed relationship and should be included in the variable. It's an information that I need to add in our model. Now, one last thought that I want to say in this scenario is that in practice, it's really hard to think of all the confounding variables that exist out there so that we can control and check, are these confounding variables or are not confounding variables. So we always need to be skeptical when we want to try to make causational conclusions about unobserved relationships. The solution to this one, and we're not really going to get into the details of that, is basically in order to be confident about talking about causational relationships, is to design an experiment. And designing an experiment where we control some stuff around the object subject that I want to study. I randomize some other stuff, and in this scenario, we will be more confident to talk about causational relationship between the variables. Anytime we have what we call observational studies, like to observe different variables, then we should be very skeptical about talking one variable causes the other one to occur. Any questions, any comments, any clarification? Okay, now what I want you to do is you go in a Google Drive. So you can find our today's handout. Let's say if you go in, week 3, there is the class activities. And then you can see here I have the lecture 3 handout. So what I want you to do is you copy the lecture 3 handout and you put, let's say you rename it, you put your university and also the names of the team members, and then you put it inside the student upload. So please copy and then put that document into this specific folder. And then this handout will give you some practice regarding confounding variables. And then you have the paper that you need to read and say some comments. But I also have an Excel activity. And in this Excel activity, I'm basically guiding you on how we're going to deal with confounding variables in the scenario of the Seattle data, the data that you used in the previous lecture. I know it may be a little bit more demanding, the Excel activity for this class, but feel free to let me know if you have any questions. Okay. So then access the third handout, start working. So I'm going to give you about 1 hour, and then in the last 20 to 30 minutes, I want you to read something, and then I want to lecture about one last topic before we finish our today's class.
And I want to remind you that most of your time should be spent on this activity, but before you leave class today, in both locations, you want to have decided who's going to be on what mock DataJam team, because you're going to have to work outside the classroom on this to come up with your proposal over the next week. Okay?
Okay, so for the Caldwell students, I want to make a comment regarding exercise 2 question 4. So for that question, I'm asking you to do a linear regression, but there is a categorical variable. So how do we deal with categorical variables? Excel cannot really tell if a variable is a categorical or is a quantitative variable. So you have the data, let's say you have the price. So you have the price, you have the square feet, and then what you need to do is you need to create 2 extra columns. The first column will be the Capitol Hill. This will be what we call a dummy variable, and it will take the value 1 if the house is in the Capitol Hill area, 0 if the house is not in Capitol Hill area. You're going to have a second dummy variable, which is the Bellevue. Again, it's going to take 1 if the house is in the Bellevue and 0 if it's not in the Bellevue area. But then, if I tell you about the third neighborhood, you don't really need to consider a third dummy variable. Because if these 2 are 0, if let's say the Capitol Hill is 0 and the Bellevue is 0, then it means it's in the third neighborhood. So your linear model will look like this one. So you're going to have the price equals to the intercept plus the slope times the square feet, and then you're going to have those 2 dummy variables. So basically, the idea is that, let's say you have the data, and you're gonna feed 3 separate linear regressions. So let's say if capital here is 1, then it means the value here will be 0. Then you're gonna have a linear regression just for the capital hill. And then if value is 1, then capital hill will be 0. Then the model will be related to the value data. And then if both of them are 0, then we're talking about the third neighborhood. You can see on the hint how you can use Excel to create those dummy variables. So please let me know if you have any questions.
I don't like this. Just ask. I think that they're organizing for their mock DataJam. But I think they're probably ready.
Okay, so are you ready, Caldwell? So we can continue a little bit with our lecture.
We're up to job finish.
R squares. Cleaners is funny. What kind of like that? What data miner?
Man,
Yeah, I didn't realize what that was.
Or in business over there.
Data miner. So.
No.
Maybe look at it.
I was like sitting there trying to figure it out for a second.
Honestly, me too. That's funny. This is. Me 22 extremely.
Next,
Internal.
What's this? What's this?
yeah.
Let's try my most. Hopefully, my tuition. You can call me Sam when I go to the store.
So, and then he says he's a sharp shooter. Because Russian master all these things.
That makes sense.
Probably benefits you. So it's like literally the thing else. Something, but it's also
Nice. Sophomore year, sorry, and I missed my entirety. So
Okay, so let's talk about what we call p-hacking and p-screening. So I'm gonna need around 20 to 25 minutes. So let's briefly talk about this one. So in lecture 2, we learn about statistical inference. We talk about confidence intervals. We talk about hypothesis testing. So these tools are useful for figuring out whether something in your data reflects an actual phenomenon or is just cause of a random chance. Now, unfortunately, hypothesis testing is not preferred. So there are different issues that they may rise with the statistical inference. So here I'm mentioning some of them. There are some false negatives, some false positives. P-values don't tell us the probability that the null is true. It's just giving us an idea of how compatible is the data with your initial guess about the parameter. There is a difference between statistical and practical significance. Let's say when you have statistically significant results, it does not really mean that these results make a difference in practice. So there is a difference between the practical significance, and there's nothing special about the threshold of 5%. So when we do a hypothesis test, we said the significance level could be used as a 5%, but we could choose 1%, 10%. So in general, there are different things that we need to be aware about hypothesis testing. And here I'm also mentioning another big problem in a hypothesis testing, which is we don't get to see all the tests that we were conducted. So this fact makes our p-values misleading and increases the chances of false positive. And we're going to see an example to understand why the p-value will be misleading in this setting, and we're going to have more false positive. Does anyone heard about Paul the Octopus? I also know, okay, I think you're too young to know about the Paul of Octopus, but here was in 2010 World Cup. And the story is that before a match, they will present to the octopus 2 boxes with the food, each one marked, let's say, with the flag of the team, let's say the country flag. Then the box that the octopus ate first, they're gonna say that that would be the predicted winner for the game. And actually, in 2008 and 2010, Paul the Octopus correctly predicted the outcome of 12 out of 14 national soccer matches. Wow, right? It's like,
Brazil was playing.
does it mean that the Octopus was like an expert in, I don't know, in the soccer, or what's going on here? Now let's statistically test the null hypothesis that Paul was no better than a coin flip. So in other words, let's assume for now that the Octopus predicting those games by random chance. Let's say 50% is going to be able to predict the winner, 50% is not going to predict the winner. Now let's find what is the probability of flipping a coin 14 times and getting heads 12 times or more. Now to find this probability, we can use what we call the binomial model. But for the people that have never heard the binomial model, we can simply see these calculations here. So basically I have the probability of correctly predicting the winner, that's 50%. If I have 14 games and I want to predict correctly 12 games, then I'm going to get the probability of predicting correctly 12 games. So I'm going to multiply that probability 12 times. So 50% to the power of 12. And then I have 2 games being not correctly predicted. And here I have 50% to the power of 2. Of course, there will be different combinations. Let's say it's predicting the first one and not the second one and all the other ones and any other kind of combinations. So here I'm using this coefficient here, which is giving you all the different combinations that we may have. Let's say maybe predicting the first 12 games correctly and the last one incorrectly, or any other combination. Now I'm doing the same business for the probability of correctly predicting 30 games. 50% to the power of 13. This is when you correctly predict the games, and then you have one game that is not correctly predicted. You get this probability, and then have the probability of predicting all the games correctly, which is basically the first one to be correct, the second one to be correct, and basically all these games, and then I'm going to have 50% to the power of 14. Now, if you add all these probabilities, you're going to see that the probability that you're going to predict 12 out of 14 games, if you randomly make guesses, 50%, then the probability is 0.0065. So it's 1 in 155. Actually, this probability is indeed very small. And that's why people, they were impressed by the results from the octopus. And that's why essentially what the calculations, the conclusions that 2 math professors did when they conducted their analysis. Now, I also want to add some extra information in our analysis, which is the following. The octopus usually predicted games involving Germany games. Okay, you mentioned about Brazil, but here I have the Germany games. So 13 out of 14 games were about Germany. He had a bias toward Germany. He chose 11 out of 13 times the Germany, but Germany also has a good team, had a good team, and won 9 out of 13 games. Now, if I incorporate that information into my calculations, and let's say try to find what is the probability that the octopus will be able to correctly predict the winner, then I need to do the following calculation. So what I'm going to do is I'm going to get what is the probability that Paul predicted Germany. That's 11 out of 13, 30 games, 11, he correctly predicted Germany. I'm going to multiply by the probability that Germany won. And then I'm going to get the probability that Paul the Octopus didn't predict Germany, and then Germany basically didn't. So this probability is going to be 0.633. That's the probability, that's the chance of correct guess by the octopus. Now let's redo the same calculations just for the Germany games using that probability. Now don't use the random chance 50%, but I'm using this estimated probability for the octopus. Now what I'm going to do is, let's say I want to find what is the probability that the octopus can correctly predict at least 11 games in this specific scenario. So I'm doing exactly the same calculations. The probability that the octopus is predicting 11 games correctly, 12 games correctly, 13 games correctly. This probability now is 0.091. So it's 1 in 11. So it's much more likely than what I had before. So this actually really improves, or let's say add evidence to why people they were impressed by the poll the octopus. Now, despite these results, we're still quite skeptical how the octopus be able to predict, let's say, the winning games in this scenario. Now I'm going to add one extra parameter in our discussion, which is what if there were 10 octopuses in the aquarium and all trying to predict the same game? Now, what is the probability that any one octopus is as accurate as Paul? So in other words, now we'll find what is the probability that at least one of the octopus is as good as Paul. So to find this probability, what I'm going to do is I'm going to get 1 minus the probability that none of the octopus correctly predict, let's say, the games. So I get 1 minus the probability that I just calculated before to the power of 10. This probability is actually 0.614. Actually, that's a very high probability. The probability of at least one octopus to be as good as Paul. Now, we also don't know how many octopuses and how many other animals they're doing these experiments. Maybe you have, I don't know, dogs, cats, they have octopuses here, they're talking about different ones, hippopotamus here, and a lot of other animals that they were doing these experiments. But as you can see, the more experiments you're conducting, the higher the probability is that at least one of them will predict some results that we want to see. And that's because of a random chance. So the more tests you're going to conduct, then you are increasing the probability that you're going to observe the expected result. Now, do we still think Paul has some power in predicting the games? Maybe no, right? Because by random chance, if we have a lot of animals, an animal will be able by random chance to predict the games. And that's exactly the same logic that exists when we're doing research, when we're conducting different experiments. Let's see what is the relationship between the example that I gave you and the projects in general. So lots of scientific results are just like Paul the octopus. They look impressive and the p-values are very low, but we don't know how many other tests were conducted, not revealed because they were not as interesting. If there are tons of experiments, then by random chance, some of them may be statistically significant. And here I have a visualization. So let's say you want to estimate this specific value here, that estimate, that unknown estimate. Now, if I report all the different values that I get for the estimates, let's say you can get something like this, like the first graph. Let's say if I take on average, I can see that it's maybe close to our estimate. But now if I'm not reporting all the results, let's say for the different animals, I don't report what happened to the other animals, I'm just reporting all for the octopus. For the octopus, what will happen is that instead of seeing the whole picture, how many tests were conducted, I'm just seeing a part of the results. And in this scenario, if I take the average result, it may be somewhere, actually maybe use a highlighter. So here, let's say the average may be somewhere here, close to what I want to estimate. But if I don't really saw the results, I see some part of the results, my estimate would be maybe somewhere here. But it's quite different than the reality. The reality is that the estimate is over here, not over there. And this is the problem that happens when we are over comparing but under-reporting the results. We're conducting a lot of experiments. We don't report the results of the experiments that are not statistically significant. I'm just reporting the statistically significant results, and then we get a very, let's say, not clear impression of the reality. Now, there are two ways that we can get publication bias. One is through a p-hacking, and the other one is through a p-screening. These are very important things that you need to know when you are working with the high school students. And let's see what are these two publication two sources of publication bias. The first one is what I call the p hacking. So an analyst knows that the result is much more interesting, exciting, and publishable if the result is statistically significant. They play around with the sample, with their specifications, until they get a significant result, and they only report that one. Not only that, also an ethical, let's say, play with the data, changing the sample size, getting specific parts of the data, but also we don't really get the real idea of what's going on in reality. So that's very a bad, let's say, thing to do when we're doing a data analysis. We also need to be aware when we're working with the high school students, we shouldn't really play with the data, modify the data, change the sample size until, let's say, we get statistically significant results. If you did an analysis and you don't have significant results, that's okay, just report. And you're gonna see actually the DataJam, there are a lot of projects that they don't show any statistically significant results, and that's fine, that's not a problem. You did your analysis, maybe the idea that you had cannot really be justified by the data. It doesn't mean there may not be relationship between the data, but maybe you don't have the appropriate data set in this scenario, or you may need to add some more, do some more experiments, or you may need to do something else to justify the observed, let's say, the hypothesized relationship that we think. And then I have the P screening, and that's the honest researchers formulate hypotheses and conduct their tests. However, the statistically significant results are more likely to be written up, published, and publicized because these results are not interesting. So now in this scenario, again, we don't really get a clear idea of the reality. So let's say if I'm investigating, I'm doing experiments about a new medicine, a new vaccine, and then there are 2,000 labs around the US that they're doing that experiment, and they don't get statistically significant results, but there is only one lab that gets statistically significant results, then it's very important to also know that there are 2,000 that they didn't get statistically significant results, and there is one that got statistically significant results. I don't want to just see the results from that one lab, because I really want to be aware that I may need to, further investigate what's going on. Is that indeed statistically significant results? Does it happen because of a random chance? Is there any problem with their sample, with the sample size? I really need to be able to further investigate what's going on in this specific scenario. Now, in both of these cases, we can end up with a lot of false positives and overlaps. So we need to be careful when we're collaborating, when we're talking with the high school students. We should not really modify, manipulate the data just to get statistically significant results. And then we can formulate a question. If you're not able to get statistically significant results, that's okay. We just need to report. We need to let people that I cannot really find any statistically significant results in this specific scenario. Now, as a statistician and in my field, there are different remedies and different ways to try to deal with those different, let's say, sources of bias. For example, we try to go away from the p-values, look more about confidence intervals, and see some more stuff in different data analysis. Not just look at p-value and see if it's less or greater than the threshold. We try to, in a lot of scenarios, reduce that significance level of 5%, so it can be a little bit more, let's say, conservative. And as I said, there's a lot of, let's say, focus now, not just looking at the p-value, but go towards the confidence intervals, effect size. So there are different things in this specific scenario. And another thing is, now, if you, let's say, submit a paper, they may ask you to be able to replicate and get the same results. So if you give me a data set, you give me like statistical analysis, I may be able to replicate your analysis and be able to get the same statistical results. Now, any questions, any comments, any clarifications? Now, on the handout, the last activity is related to P hacking and P screening. What I want you to do is basically use an AI tool let's say ChatGPT or something, and then try to further investigate a little bit about p-hacking and p-screening. Get some more information, how can I avoid these ones, and how can we help the high school students to not get into, let's say, the p-hacking or the p-screening. Any questions? Okay. So basically, I don't have anything else for today. So we're more or less done. Now, what I want you to do is make sure that you create your teams for the mock project and then fill out the Excel document, right?
Fill out the Excel document, but by next week, you want to have written your proposal and put it in the proposal folder. So you have a week to work with your team. Make sure you fill out the Excel document and put your proposal in the proposal folder.
Okay, any questions?
If you have any questions during the week, just shoot me an email. You can send it to director@thedatajam.org or jcameron@pitt.edu or datajam@thedatajam.org. All of those will get to me and I will answer your question very rapidly. Okay.
I'll see you next week.